Hi guys. So today what we're going to talk about is how we get the exponential function from the logarithmic function. In section 6.2, we came up with a rigorous way of defining the logarithm as an integral, and now we're going to look at how we can use that definition to get a definition of the exponential function. So the one thing that we're missing here is the exponential function is built out of the number e, and we haven't defined what e is yet. So we're going to start by just looking at a definition of e. So the goal for today is that we want to start with the natural log of x being equal to the integral from 1 to x of 1 over t dt. And then from that, we want to try to come up with the exponential function. And in particular, the natural exponential function, e to the x. And we're going to have to use the logarithm to do that because we're starting with a rigorous definition of the log, and we're going to try to build e to the x. The first thing we're missing is e. So what is e? If we accept our definition of the natural log, and we accept the properties that we had for the natural log. Remember that the natural log had the properties, 1, that the natural log of ab is equal to the natural log of a plus the natural log of b, and property 2, the natural log of a over b is equal to the natural log of a minus the natural log of b, and property 3, the natural log of a to the r is equal to r log a for r rational. Then the final property that we showed because of the definition here is that if we take natural log of 1, we're going to have an integral from 1 to 1, and we're going to get 0. The natural log of 1 was equal to 0. So I want to know what number creates the output 1. What x solves the natural log of x is equal to 1? And the answer is, I'm just going to define the solution to be the number e. E is the unique number, so that the natural log of e is equal to 1. And I know that number is unique because the natural log is a 1-to-1 function, which means if I can solve the equation, the answer is unique. If you think about a plot of the natural log, it looks like this. And what I'm doing is I know that point right there is at 1, 0, and I want to know where that point is, x comma 1. And what I'm doing is I'm just defining that x to be something I call e. And using Newton's method, you can actually approximate e to as many digits as you want. Now, given that I know what e is, I've got a basis to try to define the function e to the x. And e to the x and the natural log of x are how we're going to define the rest of the exponential and logarithmic functions. So what is e to the x going to be built out of? The approach that we're going to take is we're going to define exp, the exponential function, to be the function that is the inverse of the natural log. So we know that the natural log of x is 1-to-1, and we know that its domain is any number from 0 to infinity, and we know that its range is from minus infinity to infinity. And the fact that we know that the natural log is 1-to-1 and also continuous and also differentiable means that the natural log of x has a continuous, differentiable, inverse function. And we're going to call that function exp of x. So we're going to define the function exp of y to be equal to x whenever the natural log of x is equal to y. So exp is just the inverse of the natural log. And what we're going to hope is that the thing that we've defined here actually is e raised to the x power. I don't know that this is e to the x yet. I just know that it must exist because the natural log was a 1-to-1 function. And better than that, I know that whatever this is, the inverse of the natural log, must also be a continuous function because log was continuous, and it must also be differentiable because the log was differentiable. And remember that the domain and the range of the inverse are switched. So this thing has domain minus infinity to infinity and range 0 to infinity. If you want a picture of what the inverse should look like, natural log of x versus exp of x, then just like usual, if the natural log looks like this and goes through the point 1, 0, and that point right there is the point e comma 1, because remember, we defined that point to be at the point e, then the inverse function has to look like this, where that point is now the point 0, 1, and this point is the point 1 comma e, right? That these are perfect reflections of each other. So now what? We know we've got an inverse. We've got an idea of what its graph looks like. We know a couple of points on the inverse. It must exist. It has all these nice properties, but it's still sort of mysterious what it actually is. How do I compute with it? What can I do? So now we're going to use the properties of logs to show that the exp of x function must actually be e raised to the x power. Okay, so here's some properties that we're going to need. Since the natural log of 1 is equal to 0, it must be the case that exp of 0 is equal to 1. Okay, because remember, it's an inverse. Because the natural log of e is equal to 1, it must be the case that exp of 1 is equal to e, because again, it's an inverse. So what we can do is we can use the third property of logs to show that exp of a number is equal to e to that number. So let's assume that r is rational. Then it must be the case that the natural log of e to the r is equal to r times the natural log of e, which is just r. So if we stick in e to the r, then bringing the power down, at least when r is rational, forces the output to be r. So the natural log of e to the r is r natural log of e, which is just r. Well, that means the inverse relationship says that exp of r must be e to the r. The inverse of the natural log, at least when you take powers that are rational numbers, is e to the x, or e to the r. So the inverse of the natural log of x is e to the x when x is rational. Now, one of the properties of continuous functions is that because the rational numbers can approximate any real number, if a function is continuous and it has properties that hold on all the rationals, we can just extend it to all the rest of the real numbers as well. On rational numbers, exp of r is equal to e to the r, so I'm just going to extend the function so that e to the x is equal to exp of x. So we can extend to all x. And what we get is exp of x is equal to e to the x. And that's how we say that the inverse of the natural log is e to the x. So what did we show? That if f of x is equal to the natural log of x, then f inverse of x is equal to e to the x. And that's where the exponential function comes from, starting from the position of defining the log as an integral. Okay, so we also want to know where the exponential properties come from. Remember, we're not just allowed to use the exponential properties that we know when we've got a variable raised to a constant. So if we have a variable raised to a constant, I'll put these up in the corner because we know that these should be true, but we haven't proved them yet. We know that if we have x to the a times x to the b, then we get x to the a plus b. But that's for fixed constants, a and b, and for a variable x. What we'd really like to be true is that e to the x times e to the y is e to the x plus y for all x and y, where the power is the thing that's variable. So we would like e to the x times e to the y to be equal to e to the xy. And we would like e to the x divided by e to the y to be equal to e to the x minus y. And we would like e to the x to the r to be equal to e to the rx. Those are the standard properties of exponents, but in the past, we've always assumed that the variable is the base and the exponent is a constant. So we're going to have to come up with new proofs of these objects right here. The property probably most striking about the function e to the x is that the function is its own derivative. So it's a fact that the derivative of e to the x is equal to e to the x. In fact, it's the only function that has that property. So let's actually see if we can show that. So why should that be true? Well, let's use logarithmic differentiation, right? So we're going to use an implicit differentiation here. So if y is equal to e to the x, then certainly it's the case that the natural log of y is equal to the natural log of e to the x. And so it's also the case that the natural log of y, simplifying, is equal to x. Now take a derivative of both sides. So apply d by dx over here, and apply d by dx over here. And what you end up with is 1 over y times dy dx is equal to 1. Now multiply both sides by y, and you get dy dx is equal to y. But y was just e to the x. So if y is equal to e to the x, its derivative is the same. And notice what I've used here to prove that is just properties of the natural log. Okay, so if we know that the derivative of e to the x is e to the x, that also tells us that the integral relationship holds as well. So if d by dx of e to the x is equal to e to the x, then it must also be the case that the integral of e to the x dx is e to the x plus c. And just for the sake of writing it down, let's remind ourselves what exponential functions look like. Generally, if you have a function that looks like this, 0, 1, 1e, we know that the limit as x goes to infinity of e to the x is infinity. We know that the limit as x goes to minus infinity of e to the x is 0. So it's asymptotic as we head out in this direction. And that's basically our calculus properties. We have a one-to-one increasing function. We know that it goes through the point 0, 1. We know it goes through the point 1e. We know it goes up very, very quickly. We know that it tends to infinity as we go to the right. We know it tends to 0 as we go to the left. So now we're going to follow up our introduction to exponential functions with some examples. Those will be in the second video.